Time out of your day to attend this webinar. My name is Persson from Exeter. I'm in the cybersecurity group, and I'm one of the senior cybersecurity engineers responsible for assessments and implementation of some of the recommendations. I've been in the IT field for quite a while. I've also been in the cybersecurity and industrial networks field for quite a while. My most recent employment I was with MTL, which is a part of Cooper Crouse-Hinds, and then became part of Eaton Enterprises, Cooper Crouse-Hinds, MTL. And my job function there originally was the IT manager for the Americas, and then I became the industrial networks and the technical support and applications manager. And in that position, I was supporting pretty much all of the network-based devices and foundation field-bus products. So I've got a long history of IT-based products in the processing control system. So it created a nice mix. So I hope you find the presentation informative and hopefully enjoyable, and hopefully not too boring and dry as toast. So most of the presentations that are given from the cybersecurity group focus on what you need to do for cybersecurity and what you need to do for an assessment. This one's going to change tack a little bit and try to give some insight into what needs to happen when the recommendations come in and you get told that it's time to implement your solutions. And implementing the solutions, again, is what I've been doing for a long time along with the cybersecurity, so I can give a little bit of insight into what needs to happen. So generally, when you talk to cybersecurity groups, the preliminary steps as called out in ISA IEC 62443, which used to be the ISA S99 series of documents, identifies a number of requirements. And among those requirements is the need to perform a cybersecurity risk assessment. And it starts out with a high-level assessment, which looks at your entire system, your entire network, and prioritizes which subsystems need to be investigated further. And then you do a detailed cybersecurity risk assessment, and the detailed assessment digs down into the network looking at specific devices. And by looking at those devices, you begin to identify which devices are the critical ones, which ones, if they have a problem, somebody attacked them, some malicious behavior caused issues with them, they would cause significant issues on your network. Well, once you do those two assessments, then you do, and the order of this can be reversed. You can go either way with it, but then there's usually a requirement for a cybersecurity vulnerability assessment. Vulnerability assessment is also called out in 62443, the S99 documents. And what this does is looks at the products that are on your network, looks at the devices, the Windows-based components, the non-Windows-based components, the network architecture, the documents, the policies, procedures, user accounts, and it identifies where the plans of the installation or the actual installation differ from the best practices and the recommendations made by ISA, the IEC 62443. This also can show gaps in where you're missing from requirements or regulations such as NERC-CIP or the NRC series or the CFATs for chemical industries, because even though they're different industries, they still have very similar requirements. So part of the vulnerability assessment gives recommendations on mitigating your issues or your gaps. And very often, these recommendations include network segmentation and network separation suggestions or requirements. So the recommendations that follow the assessment say the network should be separated into zones and conduits as per the 62443 series of documents. And so you go in and you perform your exercise, and you usually do a paper exercise first, and you do it on either your existing network or your planned installation if you're a greenfield installation. And the whole idea of this is to identify and protect either single critical assets or groups of assets if they're clustered or if you can cluster them. So as an example, and this is a very simplistic example, is you're handed, as you're doing your process, a network architecture that shows your existing architecture. And as you can see from the drawing, you've got your enterprise network up the top with your computers, your servers, your workstations, all of your people working in their offices, and the network is connected down to your 3 plants. And in the plants are a number of different Windows-based components, be they data servers, application, operative workstations, engineering workstations, and then you get down to your plant control system, which is where your SCADA, your HMI, your historians may exist. Below that, you actually get down to your network-connected controllers, your PLCs, your chart recorders, things like that. Now, again, in this network, everything is flat, and this is very, very common. This may be an oversimplification in a lot of cases, but there's also situations where we've gone into a network, and it has been a completely flat network. When you can sit at your desk in an office and you can ping a controller out in the field somewhere, and then you realize just how dangerous that can be. A situation I had just recently is they were connected to a city network, and somebody in the town library could actually get to the controllers in the device in the field, and that was we put a stop to that rather quickly. So the zoning conduit exercise. Separate critical devices into zones. Separate them so they have a common risk level or a common criticality level, and then implement some sort of a barrier device or a conduit to limit the traffic, to limit the access to those devices. The ideal, and generally this is not as often followed, but it's something that is more and more important with Windows components and the end of life of XP, and that's just not going to be updated that fast, etc., is to separate as much as you possibly can the Windows-based components from the non-Windows-based components. Your SCADA systems, your HMI, your engineering operator workstations, get those off the same local area network as your critical controlling devices, like the PLCs, the chart recorders, the SCADAs, the things that you need to run your process. If you go blind for a little while, most likely your PLCs will keep running. You may not see it right away on your screens, but your PLCs can still control the process. If your PLCs have an issue, you've lost control of your process. Much more catastrophic results could occur. So by the time you work your way down to your process control devices, the only protocols that should be getting through are those actually required by the process and control devices. I'm going to go through that a little bit as we continue this presentation. So we've gone through our exercise, we've looked at our different devices, we've looked at our different levels, and then on paper we've drawn real pretty boxes and we've drawn a bunch of lines, and we're all happy because now we have an enterprise zone that's separated from the internet. We have an enterprise zone that is separated from the plant A, B, and C zones. We've separated the control zone from both the enterprise and the plant zone, and then further down we've separated our actual controllers from the plant zone. So as you can see, the zoning conduit exercise has now created, as you move down, different restrictions on the amount of communication. And it may not be completely apparent, but if you think about your enterprise zone, you've got email, you've got web, you've got printing services, all going on in your enterprise zone. You move down to your plant zone, you don't want all that stuff going on. You want to limit what's happening in that zone to critical communications to make your plant function, or possibly historian information. Down another level of your plant control zone, you may want to talk to the historian at the level above, but on that zone you don't want your email and your internet access. You want to lock that out. You want to communicate to your controllers. At the controller level, the orange zone, that's the zone where you may only want Modbus, or only want Ethernet IP, or only want DMP3, because that's the only protocol that these controllers are going to use and understand. So everything else is being blocked by your successive levels of firewall. And that's exactly the way this is done in real life. As you move down, you're blocking out, until you get down to the point where those lower level firewalls only have 1 or 2 holes punched in them. And that's only for the actual protocols that are being sent through the firewall to the controllers, and only for the devices that need to communicate through those firewalls to the controllers. So if there's only 2 HMI or SCADA systems and 2 controllers, your rules only permit those 2 devices to communicate with those 2 controllers. It is, the more restrictive you are at this level, the more secure and the better your network is going to run. But remember, it's talked about many a time, but one of the reasons we're doing this is because it's been proven time and time again that the Ethernet controller of many PLCs is fragile. And by fragile, I mean the software stack that controls it. And what can happen, and we've seen this time after time, is if excessive network traffic gets on the network and gets to the controller, it can actually cause the controller to corrupt, to roll over and play dead, to stop running, to stop processing I/O. There's a myriad of situations that could occur when a controller is bombarded with network traffic. Now, that network traffic can come from a redundancy scheme that uses, or a communication scheme that usually has redundancy, that uses broadcast or excessive multicast messaging. It can come from a NIC card or another network device that goes defective and just starts chattering on the network. It can come from devices that use broadcast as their main means of communication. It can use, or it can come from a virus that gets into one of your Windows-based components, and viruses generally propagate by broadcasting themselves over the Ethernet network. So even though a controller can't be infected by a virus, it can be affected by the results of that virus on the network. The whole idea of this is to stop that from happening. Fix your network, let the controllers control the process. So, okay, we've done our paperwork exercise. Now what? The recommendations are to segment your network. You've looked at your original enterprise or original network diagram that was flat and not very controlled. You've gone through and you've performed a paper exercise, and you've set up where your zones are going to be and where your separations are going to be. And now you look at that paper and, of course, how do I do it? Well, with any question, the question's easy. It's the answer that takes forever. So the first thing is ask. We can probably offer you help in most of these areas. We've got experience doing the cybersecurity side. We've also got experience doing the implementation side as part of our normal work. So please ask. We'd be happy to help. So the first step, evaluate and choose your solution. Many vendors have industrial barrier devices, and there's more coming out. It used to be a rather limited offering. They're becoming more and more prevalent, and they're becoming better and better. So who do you already have a relationship with? Don't throw that away because you now have to do this zone and conduit exercise. Again, many of the people you already deal with may have some sort of a solution, or know somebody or work with somebody that does. They may partner with somebody. But they have to have a suitable solution. It has to work for what you need to do. Do you have anything proprietary operating on your network, such as fault-tolerant Ethernet from Honeywell, or any other proprietary redundancy protocol? While that won't stop you from doing an implementation, you need to know in advance what the limitations are of the devices that you want to use or may have access to versus some of these proprietary protocols. Fault-tolerant Ethernet is known to have an issue. It doesn't have an issue, but devices have an issue working with the fault-tolerant Ethernet area of the network. And so you usually don't zone those devices out from each other. And that's just knowing in advance what you have, what you can use, and where you can implement them. What's your primary control protocol? Is it Modbus TCP? Is deep packet inspection needed? And we'll go into what deep packet inspection is in a few minutes. Is it Ethernet IP? Do you need deep packet inspection for that? Is it DNP3? There's a myriad of protocols out there that different controllers use. Make sure that your device works with those protocols, as most industrial network devices do, or do you need some other specialized functionality or other specialized applications? Like, do you need VPN functionality, a remote connection into these devices? Do you need matting, where you want to separate your control network from another network and have a single address or multiple addresses at the front of it? Do you need multiple users to be able to log in and get different rule sets? depending on who the users are. Also realize some manufacturers have devices that are specifically designed for their network. Some of the notable ones, Emerson Delta V has their controller firewall, which is made to work with the Delta V system. It's made to sit down in front of the controllers. It has firmware-based rule sets, so you don't have to make any changes if you don't want to. Honeywell has a series of Tofinos specifically designed for the Honeywell control system. Triconix has a Tofino specifically designed for their system. There's a number of others that have been developed as well that are designed and approved for the control system. So you have to investigate that to make sure that the solution you get, the solution you're looking for, is a solution that will work for you. And again, several companies are now offering industrial firewalls to protect the vulnerable components of the control systems. Some of the differences are in the industrial form factor and the robustness of the units, the fact that they're electrician or control tech friendly, they don't need IT, the knowledge of industrial protocols. They can go beyond just packet filtering. They can do bigger and better things. Some of the vendors that have created these devices are Biosecurity. Now Belden has a version of the Argon Tofino. There's a Hirschman Tofino, Moxa 9000 or 8000 series, Secure Crossing Zenwall, the MTL Tofino, Phoenix Contacts mGuard, the Siemens Scalens, and there's a number of others out there. Again, the idea is, who do you have a relationship with? Use that relationship to find the best product that suits your needs. Some general requirements that you're looking for. This may be a little bit redundant to the screen before as far as some of this stuff, but again, make sure that they are made for an industrial network. While it's something like a Cisco firewall, for the most part, will probably work in an industrial environment. There's a lot of good reasons why you don't want to put it there. Some of the reasons are that it doesn't have, in many cases, the predefined protocol lists for industrial control systems. The fact that it's much more complex than an industrial firewall. The industrial firewalls, you want the control people, the control techs, and the control engineers to understand how these firewalls work, how to configure them, how to set them up. You don't want to have IT involved every time you want to make a change or install these firewalls. You want to make sure that the devices are something called stateful firewall. And what a stateful firewall is for both TCP and UDP communications. And if you don't know what those are, we're going to touch on how to solve that in a minute. Now, what stateful firewall says, if there's a communication in place, channel in place, that it knows where it is in that communication chain. And if someone tries to jump in the middle, it understands that that person shouldn't be there, and it blocks that communication. They should be able to handle what's called non-IP protocols. We're most familiar with in the computer world today are our IP address-based communications. Most familiar with either a 10 address or a 192.168. Well, there are a lot of protocols flying around your network that don't use those IP addresses. They use the MAC address of the system. So those protocols are different. They are handled different, they work different, and they get firewalled differently. A lot of firewalls can't handle them. They don't know what to do with them, so they just block them by default. The problem is some of them are valuable. Some of them are needed in order to make your network function or your control system function correctly. So it has to be able to handle the non-IP protocols. It has to be able to rate limit. A good example is something called ARP. ARP is finding out what address corresponds to, what MAC address corresponds to what IP address. Well, in a broadcast storm, sometimes ARP is used as your broadcast storm medium or functionality. Well, if you rate limit how many ARP requests get through to the end device, you can keep that device from being affected by the broadcast storm. You also, like I said just a second ago, you want to be able to firewall the non-IP protocols. You may want them to pass, you may want them to block, but you need the functionality of being able to firewall them. The industrial design of these firewalls is different than your enterprise or your computer center firewalls. They have an extended temperature range. They're made to go out where it's down and dirty. They're made to go out and sit in the field. They're not meant to be in a controlled environment, sitting in a nice computer closet with their air conditioning and their controlled humidity, where they have their little boat drink with the umbrella. These things are made to go out where it's dirty. They're made to go out where it's dusty. They're made to go out where it's hot, where it's cold, where it's moist, where it's dry. They're made to work there. Most of them are DIN mountable. You can sit them on the rack right next to your controllers, right next to your temperature gauges, right next to your chart recorders. They do not have fans. They're all built as convection cooling. You don't want to draw in that environment and coat your components with dust or silt or whatever. So they're either sealed completely, or they have very directional cooling fins, so you get convection cooling without fans. They run off dual DC power supplies. If a supply fails, it simply runs off the other one with no interruption of functionality. They have some sort of a secure interface, be it web or be it centralized. You need to be able to get to it in a secure and controlled manner. They also offer extended functions, such as deep packet inspection, which again I'll hit in a second, virtual private networking, that remote connection, NATing, syslog services, things like that. So these devices, while they in many ways are similar to your enterprise firewalls, in many ways, as shown here, they are radically different. They're made to go out in the field. They're made to sit in front of the devices. They're made to be worked on by people who are not responsible on a daily basis for working on firewalls. And that's a huge one, because you need to be comfortable with what you're doing in order to do it effectively. So some devices that are out there, I mentioned the list earlier. I did some research on a number of devices that I had access to. So here's a small table to sort of give an idea of what's out there, what they can do, what they can't do. The table across the top is whether they have Modbus deep packet inspection, Ethernet IP, deep packet inspection. Do they have NATing capabilities, which allows you to put a number of devices behind a single IP address, such as your home router does NATing. Whether they have a web interface or a central console. Layer 2, which is a non-routing layer of the network, or Layer 3, which is a routing layer of the network, and whether they have VPN or remote access functionality. And some of the devices that I looked at were the whole Tofino family, the Moxa 8 and 900 series, Phoenix Contacts mGuard, and the Zenwall appliance. Some of the major differences is, while all three of the Tofino and the Moxa devices offer some sort of deep packet inspection, Moxa's just came out with a new rev today that I haven't even had a chance to look at yet. It came out yesterday, which is reported to fix some of the issues that they had with their initial rev of deep packet inspection for Modbus. Tofino is coming out with an Ethernet IP hopefully this year. The Moxa and the Phoenix mGuard can both do NATing and VPNing, as the Tofino can do VPN as well. The Moxa and Phoenix work off a web interface where you connect to the device itself and you do your configuration. The Tofino family has a centralized management platform where you use a single software package to communicate to a number of end devices. The Moxa and the Phoenix both have the functionality where you can switch between a Layer 2 function and a Layer 3 function. And they actually, the functionality of the devices change. I'm not going to give a lot of specifics on how they change, but the way the device works changes as you go from a Layer 2 to a Layer 3 device. And again, this goes back to investigate what you need, investigate how it works, talk to the people you already have a relationship with, get as much information, and if you need help, we'll be happy to help you. As Exeter, we'll be happy to help you with some of these investigations and decisions. Some examples of the screens that you may see. This is the Moxa Layer 3 or routing firewall, where you can where it's set up by IP address. You can define the protocol that's allowed to pass, allowed or blocked, etc., etc. Standardized firewall functionality found in almost all of the devices. This is an example of Moxa's deep packet inspection, where you can see down the bottom in the first line, I'm allowing only the read coils or read inputs to be read through from address 1 through 50. And in the second line, I'm blocking everything else that tries to come through. So in this firewall rule set, the only thing I'm going to allow are those 50 inputs to be read and returned back to my requesting device. Anything that tries to write, anything that tries to read outside of that range will all be blocked. The communication won't go through to the end device. This is an example of the deep packet inspection that I had mentioned earlier. It gives a lot more granular control over what can happen to the end device. Moxa's Layer 2 firewall, you can set up a rule set for non-IP-based protocols, in other words, protocols that do not use an IP address. When you get into Layer 2 or non-IP firewall rules, it takes a little bit more investigation. These are not the normal ones these are not the normal ones people work with. They're absolutely normal for a network. They are always going on in a network. People don't work with them as often because they're used to working with IP-based protocols and the controller-based protocols. Phoenix Contact's mGuard, very extensive configuration available with this. Again, this is the Moxa, and both the Phoenix can be a Layer 2 or a Layer 3 device, depending on how you select the configuration. You can do a lot of configuration with this one as well. The mGuard rule set, this one only has a firewall that works in the Layer 3 or IP range. You can't do non-IP protocols with the mGuard. Second step, the first step was selecting your devices and your vendor and who you want to work with. Second step, receive training. This is imperative. Some of the training that you should be looking into, basic or an advanced networking technology. How does my network actually work? What's going on my network? Who's talking to who? How often is it talking? What's happening? How is it laid out? What are these devices that are hanging off my network? This is a normal learning curve that needs to happen because IT people deal with their enterprise network. Controls people deal with their PLCs. There's a gap. This gap is, I've hung my PLC on my network, and it works, but I don't know how. And now I've got to barrier it. I've got to put something in front of it, but I don't know how the network works. Training can help alleviate that situation. After you know how your network works, you move into the device that you've selected. How does it work? What are its idiosyncrasies? How do I configure it? How do I set it up? Where should I put it? How should I put it there? Should I just put it in live, etc., etc.? So receive specific training on the device that you've selected. Then sit there and test your ability to configure the device. Use a demo kit. Use a test network. Use a PLC just sitting there with the very device in front of it. And get comfortable with how that device works. What's going to happen when you make rule changes? What's going to happen when you set it up? What's going to happen when you block things? How do I see what protocols are running? What are those protocols? Do I need them? Do I not need them? So all of these things make you comfortable with what you're about to do for real. When you feel comfortable, and usually as a ballpark, generally it's about a half a day or so, depending on the level of walking in, about a half day of networking technology, and give or take about a half day of device and test scenario setups. After that, you need to install the devices in the live or a running test network and examine the network traffic. See what's going on. See what's happening on the network. Determine what traffic you're going to have to allow to pass through to your end device. Determine what traffic is on the network that you can't do anything about, but you don't want to see every time it happens. A good example of that is Windows is an extremely chatty operating system. Hey, I've got a printer. Hey, I've got a disk drive. Hey, my name is this. Hey, what's your name? So you don't want to see all that traffic every time it happens. So you want to put in a number of rules that get rid of that traffic, but don't tell you every time it happens. And those are called deny-no logs. Again, we can provide training on a lot of these devices, on the networking, and bring you up to speed faster to allow you to get these devices online more effectively. So the third step, now you've selected your devices, You've received training. Now it's time to actually start looking at what's happening. So one of the major steps is being able to see the traffic that's getting to your devices. It's key to a successful implementation. On your switches, almost all intelligent switches are able to port mirror. And what port mirroring is, for those that aren't sure, is you're able to take traffic that in this case is going out to the PLC on the bottom and mirror that traffic to a computer that's running an application called Wireshark in this case. What Wireshark will do, and what the port mirroring will do, and Wireshark will do, is take all that traffic that's going to a PLC, mirror it to my Wireshark computer, and let you see what's happening. You can see what devices are communicating, you can see what protocol it's using, you can see the broadcasting going on in your network, and now you begin to get an idea of what's going on in your network. And it's always surprising. It is never straightforward. Wireshark can give you a lot of information. In the top screen, those are multicast messages. Multicast messages are generally messages sent from one device talking to a lot of devices at once. It's a subset of a broadcast. What a broadcast is a message sent out by one device, and it talks to all devices in the network. There's usually a lot of that going on as well. So those are the ones you see on the top screen are unwanted ones. There's something going on. In this case, it's an Entron device that's broadcasting or multicasting across the network. Is it needed? Probably not. In this case, we found out these switches were configured incorrectly. We reconfigured them, got rid of all this multicast or broadcast messaging, cleaned the network up tremendously. The middle screen is Ethernet IP. Well, Ethernet IP uses multicast messaging to communicate with its target devices. So in this case, is this transmission necessary? Absolutely. This is what's controlling your process. So you want this messaging. But you don't want to see it every time it happens. You want to allow it to go through and just be done with it. The bottom one, very similar, shows Delta V multicast messaging. Is this necessary? Absolutely. This is the message that's again, the messaging that's required to run your process. So this messaging has got to get through to its end devices as well. In the middle one, second one from the bottom, is a good example of what you may not want to get through to your end devices. In this case, this is spanning tree. Spanning tree is intelligent switches trying to find their peers to set up a redundant network. Does that need to get down to a PLC? Probably not. So you want to make sure it doesn't, but you don't want to see it every time it does, because you may not be able to configure the switches to get rid of it. So the fourth step, implement your solution. We're going to go back. We're going to say we selected our devices. We received training on it. We sat there and we looked at our network and we tried to figure out what was going on and who was talking to who. Now it's time to let the rubber hit the road. Now we're going to implement our solution. The screens to follow, since I had to have something to use to be able to show some examples, are done using a Tofino Argon demo kit by Byers, now part of Belden. And it's a Wago PLC, it's a CMP, which is a central management console, and I've loaded 3 of the modules onto it, the Firewall, Secure Asset Management, and the Modbus Enforcer, and a little demonstration to give me some traffic on the network. And again, this Exida does cybersecurity services. I should point this out. I should have said this earlier. Exida performs services, cybersecurity services, functional safety services, alarm management and rationalization services. We don't sell anything. We stay as vendor agnostic as we can, which is why I've contacted a number of different vendors and asked them if they would give me one of their products so I can do exactly this. So I can set it up, so I can test it, see what its idiosyncrasies are, make it work, try to break it. I don't recommend one over the other. They all have their definite gains. They all have their definite minuses. But what we can do is you find out who works best for you. We can help you with that, but it's up to you to find your solution. Once you find the solution, if you want help implementing it, we're more than happy to help. So again, the reason I did this with the Argon is because I had the demo kit, I had the setup, and it was very easy to get the screens I need to show this example. But this is not an endorsement specifically for the Argon series or the Tofino series of products. That was my fine print. So one of the first things you need to do when you're working with your network is to set up what you think your network looks like. And this is specific to the Tofino setup, where the CMP generates its rules based on its virtual networking setup inside the CMP and then writes those out to the Tofino. So I went through and I set up a very simple network saying my Tofino is in front of my Wago PLC, and on my unprotected port, which most of these firewalls have, I have a CMP, I have an HMI, and I have a number of other devices that may or may not communicate through the Tofino to the PLC. Regardless, they're on the network. They may be communicating somewhere. So now I figure out what modules I want to use. So in this case, I've done the firewall, the Modbus enforcer, and the secure asset management module. And these give me different functionality and different pieces of information. So then if I just simply load the firewall and I activate the Tofino, it becomes its own sniffer essentially. And instead of having to port mirror a device, I can use the Tofino in this case to give me the traffic that's trying to pass through to the end device. So I suddenly get screenfuls of information. And this is where the fun begins, because now you have to start identifying what traffic is valid, what traffic is not valid, and what traffic we just don't want to see to begin with. So we start breaking it all down. Some of it's really obvious. In this case, I've got some Modbus traffic going from my HMI to my Wago PLC. And you can see just above the blue line, the HMI, it's incoming, which is from the unprotected to the protected port, which is pretty much standard nomenclature for these firewall devices, going to my Wago PLC. So I know that's good traffic because that's my control traffic. That's the stuff I need to run my process. Excellent. I've got my first piece of information, my source, my destination, and my protocol. Then I've got some non-IP traffic going on. In this case, it knows its spanning tree protocol. Okay, I have a PLC that doesn't have any sort of redundancy. 99 and 9/10 of them don't. There are some that do, but in this case, this doesn't have any redundancy. So I know spanning tree is going on because I've got intelligent switches on my network. Do I need it? Depends on my network above, but I don't need it getting down to the PLC, and I don't need to see it every time it does. And in this case, this is a type of broadcast or multicast communication because it uses a special below the unknown node where the MAC address is 0180C2. That's a special MAC address which actually defines what it is. So in this case, I looked up, if you're not familiar with MAC addresses, the first three under the top unknown node, where it says untrusted network, has a MAC address of 00A01D, blah, blah, blah. Those first three octets is supposed to identify the manufacturer of the device. And in this case, by searching on the internet, and the internet is your friend, 00A01D comes back to a 6-net-based device. Now what you need to do is figure out which MAC address is at 511BF9. And if you have a big network, it may take a little bit of time, but this is telling you it's a 6-net device. That narrows it down. Most devices you can actually dig deeper and figure out which port it's connected to, but you begin investigating where this stuff is going on your network. You'll always find surprises. Trust me. Some other non-IP traffic. In this case, it has been identified as reverse ARP protocol, where normal ARP protocol has an IP address and is looking for a MAC address. Reverse ARP has a MAC address and is looking for an IP address. Not as common on the network, but again, this is part of the investigation. If you look the MAC address of all Fs, that means it's broadcast to your entire local area network. Everybody saw the same transmission. Did my PLC need it? Probably not. Or if not, you can always rate limit how often this can be sent down to this device. So again, my source address, my source node begins with 0090E8. So I went on the internet and I searched 0090E8, and I came back that address is manufactured by Moxa technology. So I know that whatever device is doing this is a Moxa device. Now I start looking for what device has the ending MAC address of 089F89. Can I get rid of that broadcasting? Can I not configure it? In which case, what can I do to get rid of it some other way by blocking it to the end device? All right, so the goal of this whole exercise of identifying the traffic, seeing where it's going, seeing what the traffic is to get rid of all the excess noise on your firewall screen, on your logs, and just start looking at the traffic that you need. So in this case, I put in rules to get rid of Cisco Discovery. I've got rid of the per VLAN spanning tree. I've got rid of the spanning tree. I've got rid of Cisco ISL, excuse me. I've put in, I haven't in this case, but I may have put in rules that got rid of Windows Net GUI, Windows Net BIOS, which use ports 135 through 139 because that broadcasts all over the network. I may put in link logic control. I may put in, I'm at a loss for what else, DHCP broadcast to block them from going down to the send device. So now what my screen is showing is just my Modbus traffic in this case. So now I can start working with that and setting that up to allow it to pass correctly. So I've set my Modbus to allow it to pass through, and I've sent it to what's called a deep packet inspection. In the Tofino, it's called the enforcer module. In the Moxa, it's called the deep packet inspection section, which is the firewall screen that we showed earlier. So in this case, I'm looking and I see that it's function code 3. Okay, I want to allow function code 3 then. Then I can look at the address, and it says it's 12288. Okay, I know I'm going to want 12288, so I put that into my rule. Then I look at the range, and it says, well, you're trying to read 100 registers. You need to account for that. Okay, so I put those 100 registers in. So I'm locking my rules down to only allow the traffic that I need to control the process. When I get done, I should not see any heartbeats unless something abnormal happens. So this is a screenshot. I'm going to go back 2 screens. This is the type of screen. Go back again. There we go. This is the screen that I saw when I first put the firewall in place. Every piece of traffic was passing through the firewall, giving me a heartbeat message. So my screen just filled up. Once I went through this exercise to clean it up, now I'm allowing my traffic to flow through that I need. I'm blocking and not telling me every time on the traffic that I don't need. And again, this could be spanning tree. This could be Windows Net GUI. I don't care. I can't solve it. I can't stop it from happening. I can stop it from getting to my end device. And I don't have to tell me every time I stopped it. I want to stop it. So now the screen is clean. Now if I get an attack on my network, if I get some intrusion, I'm going to get heartbeats on my network. I'm going to see this screen fill up again. I know something is going on. I know to take it seriously. If I had that full screen of information scrolling by continuously and something happened on my network, you're looking at a bunch of noise and trying to identify a line that's not noise. It's much, much more difficult to do. So the final steps. Now we've implemented our devices. They're sitting out there. We've run set our firewall rules. We've cleaned up our screen. First thing is notify the operations group that you're going to be playing around on the network. That's all they need is to start getting alarms in. They don't like that. So notify, hey, we're doing some work on these networks. We're going to pick this PLC group to work on first. If you get an alarm, let us know, but we know we're here doing stuff on it. Put the device in. Put a port mirroring in. Run Wireshark to collect as much traffic as you can to see all the normal and abnormal traffic that's going on your network. That could be 10 minutes. It could be half an hour. It could be a day. Depends on what happens on your network. Then you've got to sift through all that. Get rid of all the redundancy. If I have Modbus, I've got Modbus. If I have Ethernet IP, I've got an Ethernet IP. You just need to account for it once. Then set the rules in your device and set them as operational. Lock down your network. Make it active. Truly block what you want to block and pass what you need to pass. Then call the control room back or the operations group back. Hey, can you still see all the operations on your screen? Can you change a set point? Things like that. Make sure all of their pieces of the puzzle work correctly. Last line, move on to the next one. Don't try to do every single one at once. Pick one group, pick one device. Work on that one. Get that one working the way you want. Now you know how to do it. You've got a really good foundation. You've got your training. You've got one working. You know what the requirements are. Now move on to the next one. It'll take you half as much time. Generally, again, when I go on site and do training, I do the training on the networking, training on the device, training on the demo, and then we do the live network, and I'll work as much as you want. But generally, after we've done 1, 2, or 3 devices and may have 10, you're comfortable enough to go off and do the rest on your own. You don't need me there looking over your shoulder for the rest of them. But it's the comfort level of when you feel comfortable doing what you need to do. But again, pick your poison or pick your battles. Work on one at a time. Get that one running the way you want it, controlling, blocking, and then move on to the next one and repeat the process. Now remember, it's not a cookie-cutter approach because the devices behind the first one are different than the devices behind the second one. So your rule sets may be similar, but they will probably not be exactly the same. So in conclusion, the assessment that you've done, the risk assessment, the vulnerability assessment, it's just the first step. Work with vendors you already know. Find the best solution that works for you. It may be a vendor you already know and work with. It may be a new vendor. Investigate them. Find the best solution that works for you based on your network, your devices, and your protocols. Get training. Baseline networking training for somebody in a controls group to do this type of thing is absolutely imperative. You need to know what's going on in your network. You need to know how your network works. And again, there are always surprises doing this. There are devices that you didn't expect to be there. There are communications. We found network loops that they didn't know were there. It's always an educational experience. We have training and commissioning and ongoing assistance for most of the devices that I've talked about available through Exeter. One thing, and this is why I bolded it, to implement these devices incorrectly not only can give you a false sense of security that you think it's blocking what it's not, or it's blocking something that it shouldn't, but it can be dangerous. Because if your network is unexpectedly impacted, in other words, you've blocked traffic that it shouldn't block, it could have catastrophic results, which is why you take your time, you learn how to work it, you are playing with the core of your network functionality. These things work fantastic, but they need to be put in correctly. So that's the end of the presentation. I hope you found it informative and not too boring. If anybody has any questions, please use the Q&A box at the top, and I will answer them. If not, I thank you very, very much for your time. If you need more information, you can contact me at Exeter, Persson, Persson, at exeter.com, or you can contact me via I believe the web box. The web interface has a contact point. You can put some information there and contact me, and I'll be happy to answer any questions I can. I got a question in, does Exeter offer CHAZOP training? We are developing, first answer is yes, and we are also developing a cybersecurity HAZOP software called CyberFax, similar to our fax software, which will allow you to do the risk assessment with a cybersecurity tilt. What standards are relevant for the barriers? There are no, that I know of, actual U.S. or European standards. There are a couple of countries that have put them in. Generally, the usual, which is the CA or UL or all the usual safety ones. As far as standards for what they do, that I know of, there are no standards except for possibly Israel. The implementation of them is called out in the 62443, but it's not defined. In other words, it doesn't tell you where you need to put them or what you need to use. So that's where both experience and investigation comes in. So I hope that answered that question. And I've got one more that's blank. Let me know if that answered the questions. Okay, we'll wait another minute or so to see if we get any more questions in. I got a question in. Does Exeter offer audit services for security implementation? I don't like the word audit. Okay, I got another quick one in. Thanks, interesting. Have a nice evening. So thank you very much. Okay, I don't like the word audit only because generally what Exeter does in the cybersecurity side of things is an assessment type of a service. What we can do is work with you on these devices. If you have an audit bureau, we can work with them. We can certainly discuss what you're meaning by an audit service before I simply say yes or no. I don't like the word audit because I came out of an FDA environment many years ago, and when an auditor comes in the door, you can see all the doors in the hallway close. And that's not the environment that I like going into. We're an assessment. We're trying to help you make whatever you've done better or give you recommendations. And so do we have a service to assist you? Yes. In the past, we have gone through and documented firewall rules for existing firewalls, and this was like 10 firewalls. And so we look at one as a baseline and then go through all the rest of them and see what they had and how they differed, both plus and minus from the baseline. And so we documented what rules were in place. With these type of devices, we can do a very similar thing. What rules are in place, what they're trying to control, what they're not going to try to control. We do have the facilities to do both and I should have mentioned this earlier, but I didn't, I apologize, the ISA secure testing on a device. We have the facilities to do Achilles testing on a device. We also have the facilities to do what Exeter is developing called the Exeter scorecard, which what we can do is test the device based on the traffic that it can see, broadcast traffic, protocol traffic, along those lines. And we can test it with your rules in place or as a blank box. So we do have the facilities to do different services for your security implementation, whether that's an actual audit. We'll have to discuss that based on the term. Okay? Any other questions? All right, I don't see any coming in. I thank you all very much for your time. I hope you found it interesting. This will apparently be repeated at 4 o'clock this afternoon. So I hope everybody has a great day. And again, if you have any questions for me or you have any questions about these or anything else, please feel free to contact Exeter or myself, and we will certainly get back to you with an answer. Take care, and thank you, everybody.